Okay, hello everyone. I'm Lundu from Microsoft Research Asia. Today, I would like to introduce our recent work, MMGNN, Mixed Moment Graph Neural Network towards modeling neighborhood feature distribution. Graphs are generally used to describe and analyze entities with interactions in the real-world data. For example, the paper nodes and the citation relationship between papers constitute the citation network. The user nodes and the social relationship between users constitute the social network. In addition, there are many other types of real-world networks, such as traffic networks, web page networks, and knowledge graphs. In recent years, graph neural networks have been widely used for modeling graphs and learning representations for each node on the graph. And the mainstream graph neural networks follows the message passing framework, which updates node representations by aggregating information from neighboring nodes. Therefore, the modeling of neighbors plays an important role in neural networks. In previous works, many researchers have discussed and leveraged various neighborhood signals in the graph neural networks. For example, spectral-based graph neural networks transform the graph signal into the spectral domain by Fourier transform. Traditional spatial-based graph neural networks directly aggregate neighbors' features to update node representations iteratively. Also, some graph neural networks pay attention to the local structure signal on the graph to enhance the representative ability of graph neural networks. However, they ignore the modeling of the neighborhood feature distribution. In this paper, we propose to model the complete neighborhood feature distribution of the graph. Neighborhood feature distribution is an inherent property on all attributed graphs. For GNN methods, we propose that the modeling of neighborhood feature distribution should be considered instead of simply aggregating neighbor features. For example, a simple Gaussian distribution can be determined by the mean and variance statistics. And the traditional graph convolutional neural network only capture the mean static of neighborhood feature distribution. However, graphs are usually sparse and more information are needed for more complex distributions. So in this paper, we target at proposing a general method for modeling neighborhood feature distribution on the graph. So why we need to model the complete neighborhood feature distribution? We conduct analysis on the real data to prove the effectiveness of neighborhood feature distribution. First, we select three common statistics, mean, variance, and skewness, as distribution signals, and calculate these statistics on the neighborhood features for each node on the graph. Then we calculate the correlation between these signals and the node labels. Considering that node labels are discrete variable, we use mutual information and the feature discrimination index to measure the correlation between neighbor feature distribution signals and the node labels, which can be approximated by observable samples. Then we plot the two heat maps with Facebook social network, where x-axis denotes attributes and the y-axis denotes the statistics. And the deeper color in blue blocks means larger correlation. From these two figures, we can observe that the correlation between neighborhood feature distribution and the node label for different attributes are quite different. Besides, different distribution signals contribute differently to distinguish node labels. This phenomenon indicates that we should pay more attention to the modeling of the complete neighborhood feature distribution, and the power of signal statistic is quite limited. In this paper, we gave another real example. On the Facebook social network, nodes represent teachers or students, and we want to distinguish these two types of nodes. Node A is a student, and node B is a teacher. We notice that the mean values of their neighbors' feature are the same. We thus cannot distinguish the label of A and B based on the mean of their neighbors' features, and the traditional GCN will fail in such cases. However, the variance of teachers' neighborhood feature is larger than that of students, so this problem will be alleviated if we consider the variance signals. However, simple mean and variance signals are still not enough to represent other complex distributions. Therefore, a more general method to measure the feature distribution is needed. Some related works have also explored the effects of neighborhood feature distribution. For example, PNA ensembles multiple aggregators, including mean and variance, to gain better performance. NWR considers reconstructing mean of neighborhood features to enhance the vanilla graph autoencoder. Although these works have demonstrated the importance of modeling neighborhood feature distribution, they only use simple and lower order statistics such as mean or variance to represent neighborhood feature distribution. In this work, we provide a more general method. How to represent neighborhood feature distribution is a key problem in our setting. We introduce the method of moment theory to model neighborhood feature distribution by multi-ordered moments. First, let's review the background of method of moment in statistics theory. Moment generating function is an alternative specification of the probability distribution in statistics, which can uniquely determine the distribution. And the case term of its Taylor expansion is exactly the case order arranging moment. Also, there are central moment and the standard moment besides arranging moment. Based on this theory, we can use multi-order moments to determine the neighborhood feature distribution on the graph. Inspired by the method of moments, we design a novel mixed moment graph neural network, MMGN, which includes two major components, multi-order moment embedding and attention-based moment adapter. MMGN first computes multi-order moments for neighbors of each node as their signatures. Besides, an attention-based moment adapter is designed to select important moment signatures for specific node adaptively. Then we further introduce the two modules in detail. First, give an input graph with node features. We design a multi-order moment embedding module and calculate the multi-order moment signatures for each node on the graph to represent the neighborhood feature distribution. And the moments of different nodes can be computed in parallel at the aggregation step. And we select both arranging moment and central moment to represent neighborhood feature distribution. To keep numerical stability, we normalize the case order moment in the model. Besides, we set a hyperparameter for flexible model configuration of using the central moment or arranging moment. After we get signatures represent moments of different orders for each node, then we need to fuse this signature into one final representation for each node. Considering different statistics have different effects on the node classification task, we design an attention-based moment adapter that can adaptively select the important order of moments for different nodes. For each MMGN layer, we use the output node representation of the previous layer as the query vector for each node. And then we use different moment signatures output by the MME module of the current layer as key vectors. Then we compute attentions as weights of different moments for each individual nodes and compute the weighted average of multi-order moment embedding at the final node representations at this layer. Okay, to validate the performance and the generalization of our proposed method, we conduct experiments on different kinds of graph data sets, including social network, citation networks, web page network, and the image network. First, we present the results on social networks, which consist of 9 independent graphs from Facebook 100 dataset. And we can observe from Table 1 that our MMGN can significantly improve on all graphs, which demonstrates the effectiveness of our MMGN on social graphs. Besides the social network, we also conduct comprehensive experiments on other public graph datasets, including citation networks, web page, and the image network. And the proposed MMGN also gains best performance compared with current SOTA graph neural network method in the most cases. We also conduct ablation studies by removing certain components at a time. We compare our MMGN with GNs using single moment signals for message passing. And in the on-Dumbo mean in the table on Dumbo's all single moment models with their average logics. And we observe that our full MMGN always has the best performance on all the data sets. Besides, we conducted extensive experiments with different training set ratios on the Facebook social networks. As shown in Table 4, our model has the robust improvements on each split of the 5 graphs, even when the proportion of training set is small. In Figure 6, we visualize the learned attention values in MMGN on each dataset. Specifically, we make an average on the attention of different orders of moments at the average attention. And we notice that MMGN output larger weights for higher order moments on the social networks, while output larger weights for lower order moments on citation networks. This demonstrates that our MMGN can adaptively select important orders of moments for different graph datasets. Also, we validate the effect of hyperparameters in Figure 7. The results indicates that MMGN is robust according to these hyperparameters. Here is the other reference used in this slide. Finally, both our paper and the code are available online. Thanks for your attention to our paper, and welcome to reach out for further discussion. Thank you.